The intermediate value theorem is interesting because it's a pure existence theorem in that it tells us that something exists and doesn't say anything about how to find the thing. So it's a pure existence theorem. Let's demonstrate what this is about with a figure first, and then we'll go into the theorem itself. So maybe we can come up something like this. There we go. So here's a nice continuous function, right? This must be continuous. And it's continuous on some interval. Let's say some closed interval from A up to B. Okay, so here's a nice closed interval down here on the x's, and note that above this function is continuous. What this tells us, right, so we can follow this over, so here's f of A on the on the y-axis, and here's our B all the way up here, so f of B is somewhere way over here. Okay, so here's f of B. So what the intermediate value theorem tells us is we can take any point L on the y-axis between f of A and f of B and follow it back over here, and the intermediate value theorem guarantees us that there exists, that's what this backward E thing means, some C between A and B such that f of C will give us that L. Okay, so this C down here between A and B is what the intermediate value theorem guarantees us. Note that this only works if the function is continuous, which is why that's the most important part of the theorem and why it always occurs in the continuity chapter. Let's take a look at one that's not continuous and see why the intermediate value theorem fails. Maybe we have something like this. So here's a nice function, just some lines, kind of a piecewise function like so. Okay, so same thing, we'll call this f of x, but now it's not continuous. And then we could do the same thing. Well, here's our A, and how about a B over here? So we have f of A right about here, and of course f of B way, it's hard to kind of get that line going, there we go, maybe way up here. Okay, so now if we wanted to take any L, let's pick an L here, some L between f of A and f of B. Well, is there some C between A and B that gives us L when we run it through the function? So is there a C? No, there's no C that I can plug in to get f of C equal to L. There's not, it doesn't work because the function is not continuous. It's just this gaping hole right here. So note that the continuity is one of the more important features of this theorem. Okay, let's take a look at this theorem as it's actually written. So here's the intermediate value theorem in words and mathematics. Suppose f is continuous on the closed interval AB and L is a number strictly between f of A and f of B. Then there exists at least one C in the open interval AB such that f of C equals L. And if you want to use the fancy mathematical notation here, you can say there exists a C, that's what that backwards E business means, and then here for C in, you can use this element of symbol A comma B. Okay, so that's how, in a more advanced math class, because look, we don't need all these dang words, just use the symbols. So we say there exists a C in AB. So we just say there exists a C in the interval A comma B. Right, nice and compact, super mathy looking. Let's use this in a proof. So here we have the same intermediate value theorem written out, which note that this is sometimes abbreviated IVT. Okay, so in this example we want to prove that the square root of the quantity x to the fourth plus 25x cubed plus 10 equals 5 has at least one solution on the open interval 0 to 1. Now, one interesting thing to note about this is that this is not telling us to find the solution. In fact, we might not ever be able to find the solution. What the intermediate value theorem tells us is the existence of a solution, which is very different than a lot of the math that we're used to doing where we're always solving for something. Intermediate value theorem doesn't care how we solve for it or if we ever can solve for it. It just guarantees the existence of something. This is a very pure math idea. The intermediate value theorem doesn't care if we ever solve for it. It has no interest in that, right? It's just interested in showing that a solution exists and then the theorem is done. So it's an interesting approach. We're not interested in solving this problem. We're not interested in solving this for x. We just want to show that there is some solution. Okay, so let's get down to business here. First off, let's let our function, let's start to convert this into the language of the theorem. So let's let f of x be this function here. So square root of x to the 4th plus 25x cubed plus 10. Okay, so let's leave it at that. Note that this is continuous on 0, 1. Why is that the case? Well, remember that square root functions are always continuous on their domains. So as long as we're positive, we're continuous. But this is also a composition. The inner function is a polynomial, x to the 4th plus 25x cubed plus 10. Polynomials are always continuous. Furthermore, anything between 0 and 1 here, if we plug it into this polynomial, we're going to be positive, which means that the square root is not going to be problematic in any way. So any possible value we could plug in works for the polynomial, works for the square root. Composition of continuous functions is continuous, so this thing is indeed continuous. So check. You have to justify somehow that your function is continuous. It's always a little bit unclear how much you need to say at this point, but at a bare minimum, at least mention that it's continuous and make sure that it is, right? Sometimes you'll have a function that's not continuous and the IVT won't work. So make sure you're checking that as part of your proof, even if you don't go into great detail on going through exactly why it's continuous. I'd say it's enough to mention that it's continuous. Okay, so let's take a look at our a and our b. So here we have our a is 0. F of 0 is the square root of 10. Okay, so square root of 10, what is that? If we plug it in, we get about 3.2. And similarly, if we could do f of 1, okay, so now we're plugging in 1 here. That's square root of 36. Well, that's 6. So note that 5 is between these two numbers. We have 3.2. We're thinking of the y-axis here. I have no idea what this looks like, but I know on the y-axis, f of 0 gives me 3.2. F of 1 gives me 6. So 5 is strictly between those. So f of 0 is strictly less than 5, strictly less than f of 1. So let's just keep track of everything here. This 0 is our a, 1 is our b. So here is our f of a, f of 0, and f of b is 1. So we have f of a is less than our L. 5 is our L in this case. It's less than f of b. F of a is less than L is less than f of b. So that's what's going on so far. So we've met all the conditions. So the intermediate value theorem then guarantees the existence of this C. So thus, by the IVT, I'll just mention it here as part of the proof, there exists, or you can use the backwards E, which is much cooler, but I'll write it out in words here, some C in the interval 0 to 1 such that f of C equals 5. What does that mean? Well, that means that there's some number that when we plug it in here to all these x's and evaluate the square root, we get 5. Well, what does that mean? That means that this thing has a solution. So thus, this whole equation, x to the 4th plus 25 x cubed plus 10 equals 5, has a solution. At least one solution. It may have more. Let's just say in or on. Okay, on. In, on, it's the same. But are we consistent? On 0, 1. Okay, and we have proven this. We have proven it. So you can put a little proof box if you like. Some people like to do that. Some people fill them in. I'll just put the little box there. It signifies the end of a proof. Now, this is wonderful. We've proven it. We don't know what it is. I have no idea what it is. I'm not going to try to find it because we don't need it. That's not the point of the intermediate value theorem. Intermediate value just shows the existence and moves on.